In a previous video, we talked about head losses in pipes. We used the universal formula, or the Darcy-Weisbach formula, in which F was found using the Moody diagram. The determination of F depends on the Reynolds number. Yes, sir, today is the day. We'll talk about Mr. Reynolds. Let's imagine the water flowing in the interior of a pipe with an average velocity which starts at 0 and keeps increasing with time. The water velocity profile is such that the particles near the pipe walls is 0 and their velocity keeps growing until they reach the pipe axis, where it reaches the maximum value. Head losses are proportional to the kinetic energy, so low-speed particles have greater heads than the higher-speed particles and tend to change their positions in the interior of the pipe. Water viscosity won't allow these movements until a certain energy threshold is crossed, which means until a certain velocity threshold is crossed. As long as viscosity is able to prevent these exchanges, the water will flow with its particles sliding as in separate layers. We say that it's a laminar flow. When viscosity is no longer able to prevent these exchanges, turbulence or eddies will occur. We say that it's a turbulent flow. We already had an idea about those differences, but how to find a numeric way to relate the threshold condition to the transition between them? That's when we meet our friend Reynolds, Osborne Reynolds. Or, we must be fair, Sir Osborne Reynolds. We already know that average velocity is an important parameter. The greater the velocity, the greater the problem. And the diameter is also important. The greater the diameter, the greater the velocity differences will be. So, let's multiply both of them. Of course, viscosity is important. The greater the viscosity, the smaller the chance for eddies to take place inside the liquid. So, it will appear in our expression in the denominator. Let's check the units. Velocity will be meters per second, diameter will be meter, and multiplying we find squared meters per second. The viscosity will be squared meters per second. Remember the viscosity video? I'll let its link in the description. It results that the number that we find is dimensionless. That's where the ingenious Reynolds experiment happens. If you are interested in the original paper, here it is. You can find it online. It's a transparent pipe with a bell mouth inlet and a dye injector. See how it's looking? I think it's gonna work. But temperature differences could exist along the pipe. Viscosity value changes a lot with temperature. So, to prevent these differences, the entire device is submerged in water. There is a support to keep the device from falling. Okay, to maintain symmetric conditions, the dye injection will be installed like this. In the outlet, there is a flow controlling valve. This device was installed to measure the flow. There is a buoy connected to a cable and a counterweight in the other extremity. The buoy movements move the pointer, which indicates the level variation. This value times the area of the water tank divided by the time gives the flow. Now we just have to open the valve and observe what happens. Here is the Reynolds experiment device as shown in the pictures of the hydraulic books and in the internet. To simplify the explanations, we'll show the pipe and the dye injection and nothing else. If we know the flow and the diameter, we find the average velocity. If we know the kinematic viscosity, then we can calculate U times D over nu. This parameter has a name. Do you know it? Yes, congratulations! Its name is Reynolds number. If Reynolds number is less than or equal to 2000, it's laminar flow. And if Reynolds number is greater than or equal to 4000, it's turbulent flow. Between 2000 and 4000, it's hard to say. See in the Moody diagram, If Reynolds number is less or equal to 2000, it's laminar flow. And if Reynolds number is greater than or equal to 4000, it's turbulent flow. Between 2000 and 4000, it's hard to tell. There are other considerations that can be done concerning the turbulent flow, but they can't be summarized by the Reynolds number alone. We'll talk about them in other videos. Oh, and if you like this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.